Hi, my name is Baldarin Narbaev, and I'm a PhD student in computer science at UBC's Conagan campus. On behalf of my co-authors, I'm presenting our work titled NinjaPort, a multi-hand approach for VR teleportation. Teleportation is a locomotion technique that allows users to move from one location to another within a virtual environment. It is particularly useful for users with limited physical space who need to navigate larger virtual worlds. Traditionally, teleportation relies on physical controllers. With advancements in hand tracking on virtual reality headsets, controller-free, hand-based teleportation became a promising alternative. However, hand-based teleportation techniques often suffer from reduced pointing accuracy and increased effort. Prior work with techniques such as ninja cursors and multi-finger bubble had demonstrated that using multiple interactors can improve target acquisition in both 2D and 3D selection tasks. Building on this, we investigated whether similar benefits could be achieved in VR teleportation by using multiple virtual hands. We introduced NinjaPort, a novel hand-based teleportation technique that allows users to control four virtual copies of their dominant hand with rays, each positioned at a different distance. Users can quickly select a desired teleportation distance by pinching a specific finger on their non-dominant hand, with each non-thumb finger mapped to one of the four virtual hands. In NinjaPort, virtual hands are positioned along a straight directional line extending from the user's dominant wrist. We explored three spacing patterns: constant, with hands evenly spaced apart for targeting; increasing, where spacing grows with distance; and decreasing, where spacing shrinks with distance. Each mapping offers a different balance between precision and visual clarity. Additionally, we explored different ways to position virtual hands and teleportation reticles laterally relative to the directional line. We focused on two options: no offset, where hands and reticles are aligned on the directional line; and offset, where the second and fourth hands are shifted to one side to reduce visual clutter. Hence, in our first user study, we explored design parameters to determine the optimal spatial arrangement of the virtual hands. For the study, we used a task in which users were required to teleport from one location to another at varying distances. Each trial began with participants pointing to a cube placed in front of them and pinching the index finger of their non-dominant hand to start the trial. They then aimed at a circular target using one of the hand ray copies and confirmed the teleportation by pinching the corresponding finger on their non-dominant hand. Now I will show a set of videos demonstrating some of the spatial arrangements used in the study. In this video, we are using constant mapping with no offset. This time, we are using increasing mapping with offset. Finally, here we are using decreasing mapping with no offset. For the sake of time, I will focus only on the main findings. For far distances, participants spent significantly more time using increasing mapping than with the other mappings. We received participants' positive feedback for constant mapping, as they found it to be more predictable than the other mappings. They also mentioned that increasing mapping requires high precision and significant wrist movement. Some participants stated that decreasing mapping is unintuitive. Finally, offset improves visual clarity for some participants. The goal of the first user study was to determine the optimal spatial arrangement of the virtual hands. Increasing mapping performed worse at far distances in terms of teleportation time. Therefore, it was omitted. Participants generally preferred constant mapping over decreasing mapping. Offset showed no clear performance benefit, however, it was retained to reduce visual clutter. Therefore, the optimal NinjaPort configuration uses constant mapping with offset. We then conducted a second user study to examine how NinjaPort compares to a commercially available hand-based teleportation method and a research-based alternative called POSE. In this study, we used a task similar to that used in the first user study. Now I will show a set of videos demonstrating the teleportation techniques compared in this study. Standard technique is a typical controller-free single-ray teleportation method used in commercial VR. Its primary difference from a single NinjaPort ray lies in the ray magnitude, which was calibrated so that both techniques achieved comparable maximal distances when the hand was raised to its highest comfortable position. POSE is a single-ray teleportation method that adapts to the user's comfortable arm and wrist movement ranges by mapping them onto an average anthropometric model to construct the teleportation ray. Although POSE has outperformed standard technique in mid-air teleportation tasks, it hasn't yet been evaluated for ground-based teleportation. Finally, we evaluated NinjaPort teleportation technique using constant mapping with offset. For the sake of time, I will focus only on the main findings. Participants were significantly more likely to fail to complete a trial within the fixed time window when using POSE than when using NinjaPort. Participants also aimed incorrectly at a target significantly more often when using standard technique and POSE than when using NinjaPort. Additionally, participants spent significantly less time completing tasks and required less hand rotation when using NinjaPort compared to standard technique and POSE. In conclusion, this paper introduces NinjaPort, a novel multi-hand teleportation technique designed to improve navigation in immersive virtual environments. NinjaPort outperforms conventional single-ray techniques, providing faster and more accurate teleportation while reducing dominant hand rotation. With this, I would like to conclude my presentation. Thank you for your attention.